assistant. So that's a very different issue. If you think about it, poverty could be for several reasons. I mean, you could just start poor. Many of us in our own life cycle, whatever is our parental or family situation, when you start out, you essentially have a lower earnings. As you gain in experience and seniority, typically your economic status improves. So therefore, from that point of view, you can think of poverty as a life cycle poverty. Poverty could also be due to transitory shocks, and this is something we are all too familiar with from everyday life around us, that somebody gets hit with a health shock, and that family then has to sell off assets, incur lots of expenses, and that too cause a dip in income, and that too would be poverty. Thirdly, there is a taking on more sort of the prism of economic analysis. The first two things that I said are, you don't really need to be an economist to reflect on, these are certainly certain aspects of poverty, is you can think of more like structural poverty. Okay, what is structural poverty? Structural poverty is the case where essentially, even after all the life cycle issues have been played out, even after all the transitory shocks have been averaged out, there's still some level of income above which certain people do not get to rise above. And then there are, of course, measurement issues as to, ultra poor, poor, what is the poverty line, etc. But we all know, and we have read articles and books about that kind of structural poverty. Now, starting with the premise of structural poverty, there are two very fundamental kind of views that I want to, let me just preview this because the way I started. So, I will get back to the earlier parts, but since I am kind of laying down the conceptual frame following on Zarane's introduction, so let me jump a bit to this. So, if we start with that, we are not really talking about either life cycle poverty or transitory shocks. And we are really talking about poverty that are in some ways determined by certain deeper economic forces, which will not be resolved just through over time or once you average out various shocks. There is the view that, in a way, the easiest to understand would be think of the standard growth model sort of framework. Yeah? In the growth models, typically it's with respect to a country, okay, and often we take a representative agent who's, we think of that as a standard growth model where somebody in an island is accumulating something, and why island? Because we are not really looking at general equilibrium issues. You're looking at a given individual and just looking at the autarky problem, right? So even there are two kind of views of poverty, and what I plan to do in today's lecture is really drawing on some very recent work I'm doing, and it is really not meant to be an overview of the field because, of course, many other people have written on this, and my goal is not to provide a very detailed literature review simply for reasons of time constraints. But basically, we propose what we believe is one of the first sort of rigorous tests of these two views, one of which is, for lack of a better word, can be called a convergence view. What is a convergence view? Convergence is directly a term taken from the growth literature, where you say that, look, take a standard production function and think of somebody who's accumulating capital, right? We have all done it in our basic growth course. So, and you can even think of literally the solo model, right? That is one of the kind of benchmark neoclassical growth models. So, essentially what happens is, initially you start with low capital stock and you then converge to some steady state, yeah? So that sounds straightforward, but where is the poverty bit comes from? Well, the poverty bit comes from the fact that people may differ in their productivity. So the production function that you're dealing with, people may differ in their productivity. Similarly, they can differ in their preferences, for example, how much labor to supply, how much to save. And therefore, the steady state level of capital or income you reach could be driven by these parameters. So even after you've, that's why I said that the life cycle has played out. You have accumulated whatever capital you were meant to accumulate, right? All the shocks have been averaged out. You still could be reaching a level which is not very high. Why? Because your fundamentals are different. So that's the first column here. So you have different fundamentals. More common everyday way of describing it would be the case that the poor are poor because essentially their productivity levels or certain behavioral patterns are such that it's not really allowing them to reach higher steady state levels. Okay, and by behavior I literally mean behavior in the sense of observed choices. Okay, and in particular how much you save, how much labor you supply and all of that. It's not leading to a very high level of income in the steady state. Okay, so therefore this view of structural poverty will essentially try to explain poverty or what causes poverty in terms of differences in productivity levels or different in certain of these parameters that govern behavior, savings, etc. Now the other view, which is what Professor Banerjee hinted at, and is right that this is one of the core things about this particular paper on which this talk is based, is the idea that, well, that may be true. I mean, who can deny that parameters typically tend to be different? But if we have to explain this huge difference between, say, the wealth level of an Ambani with the wealth level of an agricultural laborer in, say, rural India, is that really driven by productivity parameter only, or is it just driven by savings propensity? Yeah. So, of course, there is a whole distribution, but with that distributional argument, you still should not be having this big gaps in income levels. And you can do standard calibration to show this. That is, it's the standard argument about if Lucas made about capital flowing from one country to the other. That look, if productivity levels were the same, say between a capital-rich country and a capital-poor country, then the rates of return would be hugely different, with a capital-scarce country having a hugely higher rate of return, and therefore there's something else that has to give. And typically the idea that macroeconomists often focus on is that the productivity levels, which is kind of a bit of a, what can you say, black box term that can cover anything from technology to human capital to institutions to culture. You can pretty much project whatever your view of what's wrong with the world into that. Okay? Now, what is a sort of slightly different view, and that too has a very distinguished heritage within economic theory, is the idea that, well, there may be differences in the productivity, and as we know that in theory, we take models, it's like individual gadgets. We realize that one gadget cannot do everything. A TV is good for something, a mobile phone is good for something, a chair is good for something. So we do understand that in reality, productivity differences must play a role, but could there be other mechanisms, other machines that could have provided a different outlook on poverty? And this alternative view, which as I said has a distinguished heritage, is the vicious cycle of poverty or poverty trap view, where the idea is that even if parameters were identical, so you have people with identical productivity, you have people with identical preferences, okay, so therefore according to the first point of view, fundamentals being the same means they should in the long run reach the same levels of income and capital, right? Yet, you could reach very different levels of income and capital in the long run. Why? Because the underlying premise about how markets work or how the production technology is very different from what is posited by growth models. In particular, here the idea that one of the most sort of easy examples of this would be, think of a production function, okay, which is S-shaped. Okay, I'll come to as to what could be possible foundations of that, but just assume that unlike a standard production function, think of a production function that's S-shaped. Okay? Now, what I've taken here is a very standard transition figure in growth models, which I'm sure all of you are familiar with, where I'm just simply characterizing the capital accumulation process. Okay, KT is on the horizontal axis and KT plus 1 is on the vertical axis. Okay. The thick line is a 45-degree line, okay? And this blue curve is really that equation, KT plus 1 is SA F of KT plus 1 minus delta KT, okay? What does that mean? It means capital stock this period, okay, is a function of how much you're saving out of the production. Yeah, A of FKT is the production function, that times the propensity to save, plus whatever remains the undepreciated part of capital from the previous one. It's a very standard transition equation that we use in dynamic models. Now, if you take this and look at this S-shaped kind of figure, you can see that, look, what would be a steady state? A steady state, by definition, is where, to put it somewhat lightly, the state is steady. Okay, and that's what a steady state is. Why? It means whatever you start with, you come out with the same situation. Okay, so therefore, subject to maybe, in this model we don't have shocks, but you could allow some shocks to this model. But the idea is that if you're starting with, say, a capital stock, you have 1 lakh rupees in the bank or 5,000 rupees in the bank, then roughly you've reached your steady state. Every period there is some maybe depreciation of your capital or whatever, but then you're also earning and saving out of that, and they're cancelling each other out, and you're kind of steady at that 5,000 rupees or 1 lakh rupees or whatever that might be. Yeah? So therefore, this is a neat mathematical trick to characterize the steady states, because anytime this curve intersects the 45-degree line, by definition, you start with this cave, and in the next period, you stay in that cave. Yeah? Why? Because it's the 45-degree line. What happens if you're a bit below? Well, that's not a steady state, because if you start here, right, this transition equation will tell you this will be next period's capital stock. Yeah? If you project that into the 45-degree line, then we get, the next period's capital stock. Then use that, and then you get, the capital stock in the period after, and this process would typically converge to that point, right? So as you can see in this diagram, there are really 3 steady states. Yeah, you can see one which are characterized by KL. Yeah, in the way I've drawn the axis, it is the case that KL is 0, but it doesn't have to be. You can choose the intercepts, or you can choose the sort of origin in a way that it could be some positive level. Okay, so that's just a matter of choosing units. Okay, so it doesn't literally have to be 0, or whatever it is, you normalize that to 0, and then you express the other things in positive quantities. So as you can see that there is KL and KAD and KH. These are the 3 steady states here. Let's contrast that with the standard production function. Okay, so it's the same story, but this is the case that we take in standard kind of neoclassical growth models. Like this is literally the solo model. Okay, and ignore this A prime and A double prime business for now. Okay, just ignore this one curve. Just focus on the A prime one. Yeah. Here, the way we have drawn it. Okay, once again there are 2 steady states. There's one at 0, and the other at this what I'm calling K star of A prime. Now, what is the fundamental difference between these 2 words? And as I said, that models are simply machines that if you put in some things into that, parameter values, it will crunch out some predictions, okay, in terms of what will happen, right? So therefore, in this model, if we take the previous one, in this model, if you input the data, right, so suppose this is indeed the true state of the world. Okay, somebody just gave us the assurance that, this is what really characterizes the accumulation process of an individual. Then what data do you need? You would say that, look, I need to know what A is, A prime is, what S is, what is the precise production function, yeah, and what is the depreciation rate. If you give me this data, I have standard tools by which I can exactly crunch out the number that characterizes K star. Okay, we know that. Take Cobb-Douglas, for example, right? Then you have an easy way, you put A on both sides, a constant K, and you just solve it out, right? We have seen it. Interesting thing though is that, and 0 is a steady state in the way I've done it, because I'm assuming the production function passes to 0, or whatever positive number that's been normalized to 0, yeah? But now let's think about the difference between that steady state and this steady state. This steady state is what is called a stable steady state. Why is it stable? Yeah, it's both a steady state. Why is it stable? Because think about it, exactly the way I put it in the other diagram. If you start with the capital stock here, yeah, you want essentially a stable steady state to be a center of gravity. It will, any deviation, it will draw back to the original state. Yeah? So if you're here, then this is going to be the capital stock next period. Yeah? And you're going to go back to that steady state. What happens if you overshoot? Suppose for whatever reason you luck out and you get an extra bit of capital. You go here, right? But then you start decumulating, because this is more than what you really want to hold in the long run, given your preferences over consumption and current and future consumption. So that's where to end. Now consider this point. Suppose you were at 0 or whatever is the positive value that's been normalized to 0. And you're hit with some positive shock because this by definition is the minimum. So negative shocks are not allowed. Okay. Now, next period you're going to go to this point. From this, you're just going to escape that. So any little shock, okay, you will basically escape that steady state. Mathematically, these are standard things that you do in difference equation setup, and indeed difference equations are what you use to solve these. And you may know from your math econ or the growth model courses that there is a technical condition that determines whether something is a stable steady state or an unstable steady state. Okay, and that has to do with the slope of this transition equation at the point it's cutting the 45-degree line. Yeah? Why? Because think about it. Here, the slope is less than 1. Sure. Okay, can you hear me better now? Okay, thank you. So, what the point of this is that essentially, if you have this slope of that curve that is less than 45 degree, in that case, essentially, shocks get dampened. You can see this, right? Yeah, it's the same way as in a linear model like Harrod-Domer, etc. You want the overall coefficient that maps next period's capital stock from this period's capital stock. That has to be less than 1 for the process to be convergent. Okay, if it's bigger than 1, it cannot stay there. It will just amplify. Yeah, it's the same thing. If you put money in your bank account, and essentially what you have is a process by which that money is exponentially growing, then that series is not converging. You want that, for that to be convergent, you want the shocks or whatever increments to dampen over time. And if you have a 45 slope, that's bigger than 1, that's where it will be an unstable steady state, right? Now, what is the prediction of this model? This model says, now let's try to apply this to reality, okay? And again, this is all hypothetical, of course, but we will, and the crux of this paper or the contribution of this paper is to derive an empirically testable prediction from these two theoretical models and then use data to throw light on which mechanism seems to be operational. So that's really what we are doing. So far, what I've told you is pretty much textbook stuff, okay? But the implication will now take from there and taking it to data. That's where our contribution, lies. So what's going on in this world is, suppose in this room, yeah, you're all representative agents living in similar environments, and all of you have an initial capital stock of K0I, I standing for the individual, I individual, M for Maitreesh, and so on, right? Okay, so if you have this whole distribution here, and assume there's some distribution, underlying distribution, some density that captures this distribution. What can we say about this economy after a couple of periods? We know that some people may have started very close to 0, but you know that they are moving away fast from that. They will, if you look at this distribution, say 10 periods from now, that there will be a gap in the distribution at that point. Okay? Whereas for the others, some of them may have started with a lot of capital, some of them may have medium level capitals. They'll all converge towards this sort of high steady state K star, K prime. Okay? And of course, in the very long run, in the absence of any shocks, you will basically have a a single point distribution where all the mass will be concentrated at that. Of course, if you add shocks in every period there can be shock, then there can be movements around. Yeah, so that's one of the predictions of this. Now let's think of this world, okay, which is captured by this particular transition equation, which in turn reflects an underlying production function that has what we economists call a non-convexity. Yeah, and the non-convexity is in the sense that if you take 2 points from the production set and you take a sort of average of that, under a standard concave production, averages can always beat the extremes. Yeah. Whereas non-convexity means if you take the average, it can be beaten by the extremes. Okay, so that's the sense in which it's a non-convex production. That means, roughly speaking, if you have to take a lottery, you're better off in a standard convex world taking the average value of it, whereas in this world, it's the classic case of the one who wins it all, because then you get to the high steady state, or you go down. There's no point staying in the middle because it's unstable anyway. That's the way to interpret it. Okay. Now let's run the same thought experiment through this diagram. Namely, on the horizontal axis, we have actual data, K0I, from a whole cross-section of individuals. And let's start with the distribution. Yeah? And then let's just run this process like a machine, and literally, if you can put this in a spreadsheet, you can literally put in a formula for the production function, right? And we put in artificial values of K0, and it's actually kind of, when I teach it, it's nice to see that you actually, it kind of, exactly what I'm saying verbally, it can play out very nicely, and you can generate that. Okay? So, in this world, what will happen? Since given all the background I've told you and your prior knowledge here, we know that in this world there are two stable steady states. Why? Because if you look at that one, if you look at that point, that is a point at which the slope of the transition equation is less than 1. Yeah? If you look at this one, this is also a point where the slope of the transition equation is less than 1. Yeah? So therefore, if there was somebody who was here, right, then next period, using this and the 45 degree line, this person will be here. Yeah? And so on, you'll go back to 0. Yeah? Whereas here, it's exactly like the solar model, because if we ignore this part of the curve and set the origin here, then this part of the curve is exactly like the solar model, like what we saw in the previous diagram. And this is another stable steady state. What about this one? Well, no, this one is a steady state, but it's an unstable steady state, because any little movement around this point, right, you either go back to that or you go up to the other. So at this point, what I want to show you is a little animation clip, very amateurish because it's made by one of us, and the credit is given there, which actually shows this using a little, I don't know if there's a, yeah, there is an empty, no, I think. So unfortunately that bit cannot be done with the PDF file. So for that I need the original PowerPoint. Okay? So let's see. Okay, let's go to, and I have already managed your expectations, so don't expect something very high-tech. That would be beyond my A parameter, but it's kind of, I really like it. My co-author Oriana Bandera did it, and she, we are friends, so she insists that credit should be given because it took her a while to do it. So this is a case of essentially these stick figures, okay, yeah. And that's the concave production function equivalent, yeah? So if I press this, and this is the moment, I hope we do not have any, quick time not available. So sadly, it doesn't happen. So I can only describe what would have happened. You would have seen that these two stick figures are actually climbing up the hill, and they're both reaching at the top, and then it looks like they're high-fiving each other, but that I think is unintentional. In the way the animation was done, and it was exactly done in the way that Walt Disney made his original animation. You do a number of these handwritten things, and you feed it into the scanner, and then that sort of creates an impression of animation. Now, since I can't do the play here of this, I'm sorry, then I'll tell you what would happen in the other case. Actually, let me skip that. Anyway, so if you take the concave, the sort of the S-shaped curve, okay, what would happen is, let me go back to, so that was unfortunate, but anyway. So if you take this, here the animation would not play, but anyway, the animation would have looked like this. So there the story is, if you look at these two and they are climbing up that S-shaped curve, right? Yeah, you will see that this person would go up to this and fall, whereas this person would go up and stay on the top. Yeah, in a way, it's a very classic sort of, it's of course meant to be a bit of a light-hearted way of looking at this thing. Yeah, but it actually captures something very literal, because if you think about the poverty trap argument, this is what's really going on. Basically, think about your economic status, yeah, as the geographic counterpart of that economic status. You're at a low level, yeah, and you want to go up. Yeah, exactly like you want to climb up a mountain, you want to go up. Now, the solo worldview or the neoclassical growth model worldview is, when you start climbing up, you're like wearing those sneakers that basketball players wear. You're getting a bounce initially, and after that it sort of flattens out, because the law of gravity means you can't really speed up too much. Therefore, those who are starting from below are actually going to run faster than you. That's exactly why if you start with a low level of capital stock, your growth rate would be high, because at that point the rates of return are pretty high. After that, exactly, if you're running up a mountain like this, eventually you will decelerate, because gravity will work on you and you can run less and less fast. And therefore, it's immediate in the construction of this that the person who's starting from below will have to catch up. And therefore, the only theory for having persistent differences in income levels has to be that the structure of the mountains are different. So maybe they're both climbing up a similar thing, but one had a higher peak because of the parameters being different and so on. Whereas the other one is literally a case that you're like stuck in a bit of a, the bottom of the hill, and initially the climb is very steep. Once you get a bit of a push, you can then sort of go up and catch up with the others, but that initial push, in the absence of it, however hard you try, you slide back. Okay, so you can think of this as okay. So essentially, this provides a canonical mechanism, because so far I've just told you there are two different production functions. I have not told you what is behind those production functions. Why does one look concave? Why does the other look S-shaped? And there are alternative technological stories that can explain that. And the one that we focus on, and this is the one that's confirmed, or this is the most support in the data, is the following. Think about production functions that basically involves you need some minimum level of capital to get traction. It's not hard to think. S-shape is of course a stylized geometric representation. We use it because it looks nice and actually there's empirical support. But think of any situation. Think of setting up a tea shop on the coffee and the College Street pavement. Okay, and assume there's space for that, which is already an unrealistic assumption. But think about it. If you literally take the solo model or the neoclassical growth model literally, it says you should be able to rent a 1 square inch space too, if that's how much capital you have. Now that's absurd, right? Because think about what the solo model is saying. This is of course a one input production function. Take the n input counterpart of it. Yeah, your f is a function of say n inputs. What it's saying is, if you actually have very low amounts of all of this, of course your total output will be low, but your marginal returns of all these inputs would be high. Yeah, and it's possible to do it. Whereas if you really think about it, it's impossible to start thinking of setting up even a most basic kind of tea stall unless you have, 5 square feet space to keep your wear, right? And that is an example. That means if you take the capital that is needed, right, to rent that 5 square feet area, that's a lumpy amount already. If you don't have that much, you'll have to be stuck doing whatever you were doing before, which presumably is not high return. So that's an example of a non-convexity. Yeah, if you think about it, in a convex world, it should never happen, because in a convex world, it says being small is no disadvantage. It's only a disadvantage at the level, but it's not a disadvantage in terms of catching up or growth. Yeah, it's a bit like being a young kid is no disadvantage. Of course, in the short run, it's a disadvantage. The kid cannot do various things, but we know the kid will eventually grow up and do just as well and possibly better than the adults. Yeah. Whereas this story is that of a stunting. It's some kid who never really got to grow up because, and again, I'm giving you an analogy or a metaphor which kind of rings true. Right? That if you think of poverty as a stunting of potential, is the classic thing that because you did not receive that big push, yeah, whether your physical stature, there's evidence of that too, but your economic stature is equivalent to of that of stunting. That whatever your true production potential was, you're going to be present. Okay? Now, therefore, production non-convexities or technological non-convexities are a leading candidate for explaining these kind of why the transition equation could look like that. By the way, what does that S-shaped thing remind you of in economics? Have you encountered something like that? It's called a learning curve. So if you think about examples of that kind of a function, it means at very low levels, yeah, suppose you're doing some activity, your learning potential is extremely high, and then eventually it flattens out. All the technology adoption, if you just Google technology adoption curve, yeah, typically people fit that kind of a curve for technology adoption, right? That essentially, initially when others are adopting something, adoption goes up fast, and then some diminishing return set. Okay? And you can think of this learning by doing. That was the example given by Kenneth Arrow, who was among the people who kind of popularized this within economics, is an example of non-convexity, but it doesn't have to be that particular form. As I told you, another production function would be just the standard Cobb-Douglas, but you only get to A, say k to the power alpha, yeah, only if k is greater than or equal to some k lower bar. If you don't have k lower bar, it's some constant amount, say, and we can call it, say, y lower bar. Why? Because you're just using your labor, you're working as a day laborer, and that's where you're stuck, your income is stuck. But if you have that k lower bar, then you can get to that productive part of it. Now, what is the missing part to this story if you want to try to essentially come up with a theory of poverty traps and persistent poverty, or as the title puts it, why do implicitly some people stay poor? Why is poverty persistent? The other bit is, what about markets? Since so far, I just took a Robinson Crusoe-like autarky model. There is no market, because market takes more than one. Yeah, market is a social institution, social and economic institution. That means you cannot have a single person and think they're conceptualized about it. But if you have a market, right, then go back to that original example I gave you. All of you have different levels of Bayesian. Some high, some low, and there's a whole distribution. Earlier, I assumed you're all living in an island and there's no way you can interact with each other. Then the story was, under a poverty